Chapter 16, Spontaneity, Entropy, and Free Energy. This is really the thermochemistry chapter you should have gotten back in Gen Chem. I think it makes a lot more sense to kind of start out here, but then again, I see the advantage of what they did, which is kind of easing you all into this. But we have 9 sections in this chapter. We're first talk about spontaneity and the spontaneous processes and entropy. Then we'll look at entropy and the law of thermodynamics, the second law of thermodynamics. 16.3, the effect of temperature on spontaneity. 16.4, free energy. 16.5, entropy changes in chemical reactions. 16.6, free energy in chemical reactions. That's really where the money is, right? This is the most important thing in this chapter. This is going to start to tie together all of the things that we've seen so far with both kinetics and equilibria, and we saw the stuff that was acid base, and it was solubility, and those are really just specialized, specific cases of some of those other things. And this is where we're going to see how everything is really all about the energy, just like Gen Chem 1, it was all about electrons. Now we're all about energy, and this is that chapter that ties it together. 16.7, the dependence of free energy on pressure, a little bit of free energy and equilibrium, and then free energy and work. So there's a lot of misunderstandings out there about the different laws of thermodynamics. You probably have come across some of them. You might even know some of them. We're going to go over them as well. We address this idea and concept of entropy very, very early on, right? So the idea that oranges are all going to sort themselves out into this. When you put them down into a container, they're going to find the lowest possible energy conformation. So they're always going to kind of arrange themselves into a hexagonal close-packed lattice for the most part. Is that entropy working, or is it that oranges are lazy that they always do this? And really, it's just how the energy works, right? So one of my favorite Simpsons clips of all time is the "In this house we obey the laws of thermodynamics" one, where Lisa builds a perpetual motion machine. So sometimes you will see things where people are talking about perpetual motion machines or 0-point energy or quantum stuff. And that's, I feel, a very big and important part of my job is to kind of inoculate you against people who are trying to exploit ignorance for money, right? So there is no such thing as a perpetual motion machine. Sorry. It's a kind of funny subject. So the first time you go through it, you don't understand it. And the second time you go through it, you think you understand it, except for 1 or 2 small points. By the third time you go through it, you know you don't understand it, but by that time you're used to it, and it doesn't bother you anymore. Kind of a lot like quantum mechanics. So nothing in life is certain except for death, taxes, and the second law of thermodynamics. All 3 are processes in which useful or accessible forms of some quantity, such as energy or money, are transformed into useless, inaccessible forms of the same quantity. And that is not to say that these 3 processes don't have fringe benefits. Taxes pay for roads and schools. The second law of thermodynamics drives cars, computers, and metabolism. And death, at the very least, opens up tenured faculty positions. That's Seth Lloyd writing in Nature in 2004. So there are 3, sometimes 4, basic laws of thermodynamics. The 0th law says that if 2 thermodynamic systems are in thermal equilibrium with a third, then they are in thermal equilibrium with each other. The first law says that energy can neither be created nor destroyed. It can only change forms, so that at any process, the total energy of the universe remains the same. The second law of thermodynamics says that the entropy of an isolated system, not in equilibrium, will tend to increase over time, approaching a maximum value. Die Entropie der Welt strebt einem Maximum zu, if you wanted to do that in German. All right, things fall apart. The entropy of the universe tends to maximize. And the third law of thermodynamics says that as temperature approaches absolute 0, the entropy of a system approaches a constant minimum. We can rephrase these as: you must play the game, you cannot win, you always lose, and you can't get out of the game. So let's talk about a chemical reaction. We're going to talk about spontaneity. chemical reaction requires both thermodynamics and kinetics. The chemical kinetics focuses on the pathway between the reactants and the products and determines the reaction rate, how fast it is. So you guys should remember this diagram here where we've got reaction progress on X and energy on Y. And we start off with the reactants having a certain amount of energy and they need to overcome the activation energy barrier to form the products. So if you look at this process of going from one thing to the other, we said that was kinetics, right? And that's related to this energy here, right? And then going from the reactants to the products and looking at their overall change, right? Because we could catalyze this, put in a second intermediate, or come up with a different reaction pathway, which would change the kinetics. Then looking at our reactants energy and our products energy, that's the domain of thermodynamics, our final and our initial states. So remember those state functions versus path functions from back in the day? Yeah, that's going to be something that's tied into the thermodynamics, or the chemical energy of the system. Right, so our thermodynamics, because we're looking at products and reactants, that's our big K, that's equilibrium. And it's going to tell us and help us predict the direction in which a particular process will occur. It doesn't tell us anything about the speed of the process, right? Because that's kinetics, that's little k. Right, so this little diagram here is going to tell you which is big K on the edges and which is little k on the inside. And they're both related to energy, right? So spontaneous does not mean fast, right? So diamonds are forever, but not at STP, right? The rusting of these wheels, for example, is a slow but spontaneous reaction. If I take that iron and I increase its surface area and I have got steel wool and I set that on fire, that's a fast spontaneous oxidation of iron. It's the same process, right? They just happen at two different speeds. So let's look at some spontaneous versus non-spontaneous processes. So ice melting at room temperature is a spontaneous process, right? The non-spontaneous process would be water freezing at room temperature. A spontaneous process would be sodium metal reacting violently with water to produce sodium hydroxide and hydrogen gas. The non-spontaneous process is sodium hydroxide reacting with hydrogen gas to produce sodium metal and water. The spontaneous process is ball rolling down a hill. Right? The non-spontaneous process is a ball rolling up the hill. Right? Rusting of iron at room temperature, spontaneous. The conversion of rust back into iron metal at room temperature, non-spontaneous. Water freezing at minus 10 degrees C is spontaneous. And the non-spontaneous process is ice melting at minus 10 degrees C. And notice that these are independent of whether it's exothermic or endothermic. Right? The endothermicity or exothermicity, the delta change in enthalpy, delta H change in enthalpy, could be positive or it could be negative. We've got spontaneous reactions that do both. Right? And we're going to see that entropy is really the tiebreaker there. So things kind of favor those exothermic reactions, but entropy could take over and be the dominant one. So you can't just look at something, go endothermic, exothermic, it's spontaneous, right? Better than average odds, exothermic will be, endothermic won't be, but you can't stake your life on it. Right? So, for example, here's a clicker question. Which of the following is a spontaneous process? Pause. Answer it. Yeah, very straightforward. It's the iron rusting at room temperature. All the others are non-spontaneous. So let's remind ourselves about our state functions again. So enthalpy, entropy, and spontaneous processes. Enthalpy is a state function. Entropy is going to be a state function. So a state function is a function or property whose value depends only on the present state or condition of the system and not at the path used to arrive at that state. So you guys have seen delta H a lot, right? You're always going to do it final minus initial, right? It's the heat change in a reaction or a process at constant temperature. So delta H is equal to delta E plus P times V, right? That little bit of PV work that happens. Entropy is the amount of molecular randomness in a system. And I wrote over here lie, because I'm going to talk about what entropy really is, because I'm that kind of chemist. It can be thought of as a measure of the disorder of a system or as chaos. All right, so you can think of it that way, but that's not the real story. A path function, on the other hand, is a function or property whose value does depend on the steps taken between the final and initial states. For example, work, or if you're climbing up the mountain, the number of footsteps you had. All right, if you're going on the windy trail versus the straight trail. That's a path function. Which path do you take? State function would be, well, what is your change in altitude? Let's take a second to talk about probability. What's the chance order that the cards can be restored by reshuffling? All right, so yeah, your intuition is right. It's a very, very, very small number. That's going to involve some, factorials and exponents, and the odds are not good that you can reshuffle those things into a random order, right? Or into a particular order out of randomness. So what makes a spontaneous reaction spontaneous is that it occurs without outside intervention and is thermodynamically favored. All right, so this thermodynamically favored is what we really want to get at. You observe it by saying, oh, I didn't do anything to this system. Right? And the driving force is ultimately going to be an increase in the entropy of the universe. And it says entropy, measurable, and no, it is just wrong. Right? Just wrong. Right? Entropy is really a thermodynamic function that describes the number of arrangements that are available to a system existing at a given state. Right? The more ways a particular state can be achieved, the greater the probability of finding that state. Right? Nature spontaneously proceeds to states that have the highest probabilities of existing. So, measure of molecular randomness or disorder? No. Thermodynamic function describing the number of possible arrangements in microstates? Yes. Right? So, let's look at another example. So, expansion of an ideal gas into a vacuum is a spontaneous process in which our driving force is probability. Right, so a gas spontaneously attains that uniform distribution because there are more ways of having the gas evenly spread throughout the container than there are ways for it to be in any other possible state. Right? You don't sit in a room and whoosh, all of a sudden the oxygen's on one side. Right? It's going to be evenly distributed across as many possible states. In this case, states means a location as possible. So looking at our ideal gas, right? Our ideal gas is going to expand, and now I've got the possibility of existing here in this little volume of space, or over here in this volume of space, or in any of these possible other spaces contained on the right-hand side, and that's why gases will expand. That's why nature is going to bore a vacuum. All right. If we do a smaller number, and we look at actually writing out the possible number of microstates, having them all on the left-hand side, I've only got one possible combination where they're all on the left-hand side. I've got 4 combinations where I can have 1 on the right and 3 on the left. Right? I can have only 1 combination where they're all on the right. I can have 4 combinations where they're 3 on the right and 1 on the left. Right? But I've got 6 possible combinations where I've got 2 on either side, like A, B, and then C and D, or I could do A and C and B and D, or A and D and C and B, right? When B and C and A and D, and B and D and A and C and D and A and B. So we've got more possible states for where they are evenly distributed. And so your most next likely one would be, okay, maybe sometime I do get a little bit of uneven distribution, but nature's going to try to drive it back to this 6, and it's not going to stay in this conformation where we've got 4 because it's not as evenly distributing that. There's going to be more energy on this side than there will be on this side. So our number of microstates we're going to call n. It's a number of possible positions, and x is the possible number of molecules, and the distribution with the largest number of microstates is the most probable distribution of molecules. And that, my friends, is what entropy is really all about. Forget all of that chaos or randomness. It's about how do you distribute things as evenly as possible, and you do that because it's going to minimize the amount of energy in that system. Right. So in 1868, Stefan Boltzmann said that the entropy of a system is related to the natural log of the number of microstates W. So he said S, that's our symbol for entropy, is K times the natural log of W, the number of microstates, and where K is that Boltzmann constant. Right? And so that's a really powerful expression or description about what entropy is. It's really the number of microstates that you've got in some sort of natural log-y fashion, and then some unit here that's going to convert it into joules at a given temperature. Right? And entropy is a state function just like enthalpy is. And we're going to calculate a delta S, and most of the times we're going to be using a delta S rather than trying to find an actual entropy. Sometimes we will, but usually we're going to use a delta S. And it's going to be final minus initial. So we can rewrite this, and we can say that our change in entropy is going to be K times ln times the natural log of the final number of microstates minus K times ln minus the initial number of microstates. So if our final number of microstates is more than our initial, then our delta S will be bigger than 0, and entropy will increase. Right? We do have tables of standard entropy. So it's this absolute entropy of a substance at 1 atmosphere, and typically at 25 degrees C. So what do you notice about the entropy values for elements and compounds? All right, well, let's look at the liquid water versus gas phase water. All right? If I'm going from a liquid to a gas, notice that I have to have the states in here. The gas state is going to have way more entropy associated with it than the liquid state. It's got more space to spread out in usually. It's going to have more possible positions it can arrange itself into. So a liquid is going to have more than a gas is going to have more entropy than a liquid. And a solid is going to have less entropy than that gas, right? So in terms of increasing entropy, solid, liquid, gas. You're increasing entropy as you increase states. And if you go back to that actual equation, right, that's going to be at 25 degrees C. If you need to increase it, right, increase your temperature, then you're going to increase your entropy too. If I'm looking at different phases of graphite, right, my graphite diamond is going to have a different entropy than graphite. So graphite and diamond will have different entropies based on their conformation of those atoms. Helium and neon are pretty close to each other, right? They're both they're both going to be monatomic ideal gases, right? And so what's happening is that you've got a larger atomic radius. Entropy for gas phase is greater than that of the liquids or solid of the same substance. So I2 gas is going to have a greater entropy than I2 solid. More complex structures are going to have greater entropy. They've got more ways that they can move or bend those molecules. So C2H6 is going to have greater entropy than C2H4. And we can really get into it in PChem and talk about how many degrees of freedom and which way you can rotate those molecules and how those molecules might vibrate. But for right now, more complex, more entropy. Allotropes, more ordered forms, have lower entropy. Diamond has lower entropy than graphite because in diamond, they're all sp3 hybrid carbons. They're all locked into place. Graphite, they're in hexagonal sheets of hexagons, and those sheets can slide past each other. It allows a degree of motional repositioning that diamond would not have. When we want to calculate using standard molar entropies, we can do that the delta S naught, which is our change in standard entropies, is going to be the standard entropy of the products minus the standard entropy of the reactants. So you could say delta S naught is going to be C times the delta, the S naught of C plus D, it's the stoichiometric coefficient of D times its specific entropy, and A times A's specific entropy, and B times B's specific entropy. This equation is very, very similar to the one that you did with enthalpies of formation way back in the other thermo chapter that you did in Gen Chem 1. The difference is here now we're looking at standard state enthalpies, standard state entropies rather than standard enthalpies of formation. So let's do an example using standard molar entropies. We're going to calculate the standard entropy for the change in decomposition of N2O4. So dinitrogen tetraoxide is going to decompose into two NO gases, nitrogen dioxides. And just kind of looking at this, what do you think the entropy is going to go to? Is it going to be a positive or a negative number? Well, if I'm increasing the number of molecules, and I've got that n to the x type of formula, I'm increasing my molecules, I'm increasing that, so I should end up with more entropy. It should be a positive change. My final should be bigger than my initial. So we're going to do 2 times the standard state entropy of the nitrogen dioxide minus 1 times the standard state entropy of the dinitrogen tetraoxide. We look these guys up on the table. We get 2 moles times the entropy that we looked up minus 1 mole, because there's only 1 out there, and its value of 304. So we end up with positive 175.7 joules per Kelvin. And note that the unit is kind of a little bit unusual. It's in joules per Kelvin, right? So you got to make sure that when you're doing some more complicated things, you're able to keep track of what those units are. Right, so let's do a quick concept check. I've got 2.4 moles of gas. It's in a 4-liter bulb at a constant temperature of 32 degrees C. If the bulb is connected by a valve to an evacuated 20-liter bulb, assuming the temperature is constant, what would happen to the gas when you open the valve? I pause. Yeah, the gas should spread evenly throughout the 2 bulbs. Right? What's going to happen to the entropy of that system? Is the entropy going to increase or decrease? Yeah, it's going to go up. Right? So in our situation, given your answer to in part B that I didn't have on there, what is the driving force for this process? Right, is it going to be entropy change or enthalpy change? Or, yeah, it's an increase in the entropy of the system. So we do have this idea called positional entropy, and that depends on the positional probability. Right? This is where we get the idea that entropy equals disorder. Right? So you want things in their place in an ordered system, and things will tend to spread out in a disordered system, and we're just seeing that spreading out happen being driven by entropy, and we're kind of making that connection between order versus disorder, but really it's about this positional probability. And it depends on the number of configurations in space, or positional microstates, that yield a particular state, so gas expanding in a volume. All right. Our third law of thermodynamics is that the entropy of a perfectly ordered crystalline substance at 0 degrees K is 0. So if you've got something at high temperature, right, they've got a lot of molecular motion, there's more randomness, there's higher entropy. And I've got a broader distribution of individual molecules. At lower temperature with less molecular motion, there's a narrower distribution of molecular energies, less randomness, and lower entropy. Right. Our solids, which are nice and neatly arranged, right, in theory, into these cute little crystals. Right. Everything is in its place, nice and neatly ordered. Not very many positions things can go to. In a liquid, well, these guys are free to move around, aren't they? And go from one spot to another spot. And in a gas, they're really free to take on whatever motion they want and end up in different positions. So entropy is going to increase, right, as your state of matter goes from solid to liquid to gas. Right? and you're increasing the entropy as you go up through your temperature changes. Okay. So which of these is going to have a negative change in entropy? Dissolving salt in water, heating chlorine vapors, heating a pure liquid, or the deposition of a gas to form a solid? Pause. Okay, yeah, it's going to be the deposition of the gas to form a solid. Dissolving heat in water, you're going from something that's a nice solid crystal, distributing that out across the entire volume of the water. Heating chlorine vapors, you're going to give it more energy, you're going to increase that molecular motion. Entropy is going to be temperature dependent, so it's going to go up as temperature goes up. Heating a pure liquid, same idea that you're increasing temperature. Right? Deposition of a gas, which is, random motion gas going on, into a nice solid, right? You've decreased the volume, you've ordered your molecules, that's going to be a negative change in entropy. Which of the processes depicted to the right do you think has a positive change in entropy? A, B, C. All right, so let's take a look at A. A is this solid going to a gas. C is going to be looks like a liquid going to a solid. And this B looks like it is forming some new molecules. There's 8 and 6. All right, so it's going to be A. We're going to get the positive entropy change because we're going from a solid to a gas. A gas is always going to have more entropy than the corresponding solid. Here, going from the liquid to the solid, we're losing entropy. Here, we're going from 8 things to 6 things. My N goes down. I'm going to decrease my entropy. Right? As the number of moles increases, entropy increases. The entropy is less with the side with fewer moles than the side with more moles. So if I'm taking 2 NH3s and I'm making an N2 and 3 H2s, my entropy will go up because I've increased the number of moles. Right? So let's do another concept check. We're going to predict the sign of entropy for each of the following, and then we're going to explain. Right? Pause it. Okay. Now that you've done that, let's work through them. So in A, right, it's going to increase because a liquid is turning into a gas. You're evaporating. Freezing water is going to decrease because you're going from a liquid to a solid. Compressing an ideal gas at a constant temperature is going to be decreased. We've reduced the number of possible microstates. The volume of the container is decreasing. Heating an ideal gas at constant pressure is going to increase it because we're going to expand the volume, for one thing. We're also going to give our molecules more energy. And dissolving sodium chloride in water will increase it because we've taken that solid and dissolved it and turned it into corresponding Na plus and Cl minuses. You could view it as either I'm distributing across a broader basis for the NaCl, plus you've got the fact that you got more moles than you had in the beginning. So you're going from NaCl as a unit into Na plus and Cl minus. That right there is an increase in entropy. Plus you're taking it from a solid into something that is dissolved, also an increase in entropy. All right. So let's try another example. So for each of the following pairs, we're going to choose the substance with a higher positional entropy per mole at a given temperature. So A, solid carbon dioxide versus gaseous carbon dioxide. And B, nitrogen gas at 1 atmosphere and nitrogen gas at 1 times 10 to the minus 2 atmospheres. All right, so looking at that first one, since a mole of CO2 has a greater volume by far, the molecules have many more available positions than in solid CO2. The gas is going to have the higher positional entropy. A mole of N2 gas at 1 times 10 to the minus 2 atmosphere has a volume that's going to be 100 times that of a mole of N2 at 1 atmosphere. So the N2 has more room to spread out at that lower pressure because it's got a larger volume, higher positional entropy. All right, let's try these. We're going to predict the sign of the entropy change for each of the following processes. A, solid sugar is added to water to form a solution. And B, iodine vapor condenses on a cold surface to form crystals. Ready? So the sugar molecules are going to become more randomly dispersed in the water when the solution forms, and thus have access to a larger volume and a larger number of possible positions. The positional disorder is increased, and there will be an increase in entropy. Delta S is positive. The final state has a larger entropy than an initial. Our gaseous iodine forming a solid. We're starting off at a gas. We're going into a solid. Our volume has decreased. Our number of positions that it can occupy has reduced. So it's got a lower positional entropy. Our delta S is negative. Our entropy will decrease. So we now need to remember some definitions from before.